And the tetrahedron, you say, I would like to fill all space with tetrahedron. I'm sure the Greeks tried this out. So they put a tetrahedron in this corner, a tetrahedron here, and a tetrahedron here. Then if they put another tetrahedron in here, they found the space between these two would not accommodate a full regular tetrahedron. So I think there was very much of a propensity on the part of humanity, which is still operative, to try to explain things monologically. Man says, is that the building block? Is that the key? He likes the one thing to explain everything. Whereas just since the 20s we have complementarity, and only in 1956 we have the Nobel Prize given for demonstrating that the complementarity was not mirror images, were two fundamentally different, just the protein and the proton and the neutron always complementing one another. So I find the tetrahedron and the octahedron always complementing one another becomes utterly satisfactory. We find then that the space that you have here is...
Bucky, there's red now. There's another color.
Oh, thank you, very good. We have here then, I put the tetrahedron in here, and then we find the, I interconnect, I did this in a very peculiar way. If I interconnect this point here, and this point here, and this point here, then you see an octahedron sitting here. In other words, there's a tetrahedron, and the octahedron always complementing the tetrahedron to fill the space, fill all space. Now, I'm going to draw that with the following manner. I'm going to do tetrahedron. I'm going to give it red legs coming up towards us here. And I'm going to now then, I have the, and then we interconnect here. You see that octahedron sitting in there. Now I'm going to make a triangle which we have make it a bigger one. Very shy. This sheet is going to start fresh. I'm going to start the single tetrahedron. I'm going to not make it red like that, just like that. Then the next one I'm going to have tetrahedron here, tetrahedron here, tetrahedron here, and I'm going to use the red for the interconnecting the tops of the tetrahedra. Gives me a different plane from the black plane of the base here. Now we'll have a next size Then we're going to connect the tops of the tetrahedra. We find 3 octahedra here. As these 3 octahedra come together, this one, this one, this one, they leave a tetrahedral space with a point going inwardly. Can you see that? So I find that if I make an accounting of what is here, I have 1, 2, 3 tetra, volume of 1 each, and 1 octahedron, which has a volume of 4. So the volume there is 7. This has a volume of 1 tetrahedron. Here I have 1, 2, 3, 4, 5, 6 tetra point out towards us, 1 tetra point inwardly, and 1, 2, 3 octahedra. 3 times 4 is 12. 7. The volume of this is a plateau here now. There's a red plateau. There's a red plateau here. The volume of this is 7. The volume of this is 19. We then make even bigger one. Now I'm going to put in my octahedra, and we have 1, 1, 2, 3 tetrahedra point inwardly like that, formed from this red plateau. We have it in the counting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tetrahedra point out, and 1, 2, 3 tetrahedra point in. We have 1, 2, 3, 4, 5, 6 octahedra. 6 and 4 is 24. Have 7, 37. The volume of this truncated plateau thing is 37. So we're now going to take the 1 plus 7 equals 8. As we sit this one on top of that one, quite clearly can do that. Then I take this one sitting on top and sit them all on top of here, because this has a base of 2 and this has a plateau of 2. So it fits there very neatly. So we have then, we add the 8 of this to the 19. So 8 plus 19 equals 27. Then I take the 1, 2, 3 sitting on top of the 27 and add the 27 sitting on top of here. Because the base here is 3 and the top here is 3. So they fit. So we add the 27 plus 37 equals 64. Now that equals 2 to the third power. This equals 3 to the third power. And this equals 4 to the third power. So we can say tetrahedroning instead of cubing. And we find that the cube then takes 3 times as much space as that tetrahedron. So nature, always being most economical, should have to do it with tetrahedra. So I can then, if we're using cubes to do your counting, you can only get 8 cubes around a common point. You have 4 in the base and 4 sitting on top of it. 8 come together, common center. 90-degree clock in there. So volumetrically, you can only be 3-dimensional. But when you have tetrahedra coming together, you can get 20 tetrahedra, a volume of 20 around one common point. I can get 2 to the fourth power times 2. You can have, we can actually do fifth power models of what we're looking at here. For instance, well, I can reach this. So this is the modular edge here is 5. So you have 5 to the fifth power, 5 to the third power. Just do that, and you'll tell exactly what your volume is.